So let's get back to our example of a macroscopic system where we are basically need to estimate all of the friction losses with the turbulent flow inside of the system in order to figure out how strong of a pump we need to have to actually pump through. So we started working on the problem. So we are pumping. Is my mouse responsive? Semi-responsive? Whoops, no. We started. Is mouse now responsive? Yeah, all right. Needs to wake up apparently. So we are pumping the fluid from this bottom pan or plane. So here's my pump through this piping system to this second elevation. And essentially I have about 85 feet difference in the elevation. So I will have, we actually estimated, given the rate that we desire for flow through the system, we basically looked into the Reynolds number and figured out that, hey, this Reynolds number is in turbulent flow regime. This will help us out to find friction factors, and it's friction factors that ultimately help us out figure out the friction losses along this tubing. Now, what we have to treat separately, we did come up with the energy balance or macroscopic energy balance formula last time around. So we do have the formula, and what we need to do is we will have to break both this. So there's friction factors in different types of geometries, and we know that these things are sensitive to the type of geometry I'm flowing through. One of them is the familiar one, that is the tube. Okay, and the other one is not necessarily familiar, or we haven't worked with it. Those are the elbows, or these 90-degree turns. But there is tabulated values that one actually resorts to. It's not perfect, but it's an estimate. Okay, so first thing that we did is just basically we want 12 feet cubed per minute in my favorite unit system. I prefer SI system, but oh well, this example is not an SI system. So we are pumping water. This is the density of water in this unfamiliar type of units. So one also has to use the conversion tables, and conversion tables are between different unit systems are available in BSL if you ever need to use them. So in any event, we got to basically figure out the Reynolds number, which is in turbulent flow regime. So let's now continue with the computation of the rest. It's not difficult. It's really application of the formula. It's not also, this is not the topic we're going to spend time on a lot. And frankly, microscopic systems are my favorite. All right, so we have figured out the turbulent flow regime. Now we actually go to the energy balance, macroscopic balance, which I'm going to state once again so that we also review it. And let's see how is my, good. I did not reboot the system last night, but it's working. So my energy balance looks at difference in the square of the velocities at inlet and outlet, which good news in this case is actually we're looking for steady state, so we're looking for the same velocities since the piping diameter is the same everywhere. Right? Plus difference in essentially potential. Plus integral of 1 over rho dp. Well, good news is we have incompressible fluid water, so this will disappear as well. So let me happily, this is 0 since V1 is V2. This is not 0 elevation, there's an elevation difference, and this is 0 since incompressible. And then I have the work on fluid done by the pump, and this little hat means that I divided by mass flow rate.
May I ask you a question? That term is zero because the tanks are at the same pressure, not because it's in reverse. That term.
Oh, yes. Yes. That is the case. So same pressures, but it's going to evaluate to the same value.
Yes.
Yeah. And then I have basically sum over all of the pipe pieces. So these are my friction losses. And this is how we estimate them for each pipe, which I denote with I. So these are friction losses in pipes, or the straight segments of pipes. And our friction factor is right here. And then minus also friction losses in these elbows. And these EV, these are the tabulated values for different types of for different types of connectors, essentially in the piping system. So I'm gonna just refer to this as EVA, just to shorten it, and this is going to be EVB. Now, who can tell me what are the friction factors for a turbulent flow regime for pipes? What is the formula for it? We have the same type of pipe throughout. Same diameter. That's laminar. It is a function of Reynolds number. So it's actually 0.791 divided by Reynolds to the 1/4. That's the fitting to that Reynolds number.
So we actually have to
look it up in your chapter 6.
Yeah.
Okay. We did actually have, we had like a plot, so it's basically, you come up with it by fitting to the experiments in this range of Reynolds numbers. And we are 7 to the 10 to the 4. So over 70,000. Okay? So that's approximately, and we calculated Reynolds number as 7.11 times 10 to the 4. So this is 0.049. And for circular pipe, what is my hydraulic radius? R over 2. So area over perimeter, right? So my first term is 1/2 V squared, and the length, so basically I'm gonna sum up all of the lengths that I have, because each term has a length in there, and that's the only thing that is different from pipe to pipe. So I have 5 plus, I'm looking at the picture, and I hope you're looking at the picture you have. It's in a different thing. So the first segment is 5 plus 300 plus 100 plus 120 plus 20 feet. So this is sum of lengths of pipe segments. So my velocity term I already calculated as 2.3 feet per second last time around. So this is 2.3. So I will overall have here 85 feet square per second square. Now for EV, to calculate the second part of what is happening in this connector's elbows, I need EV, which is a tabulated value from chapter 7. So we have part that I'm entering the pump, that is a sudden contraction. And I also have sudden expansion. So contraction, expansion, exiting the pump. And I have 90-degree elbows. And the values are 0.45, 1, and 0.5. Again, look up in table in chapter 7. So then the second term, again, I have the average velocity that I'm flowing through at steady state. And I just sum up all of these EVs, and I have 3 elbows, and this entering the pump and exiting the pump. So this is this term is 1/2 times v squared 2.3 square times entering the pump, exiting the pump, and 3 times elbows, feet square per second square. Then comes to 8. So that's it. So I have my EVA, I have my EVB, and I do know elevation difference, so I can actually estimate this term, which is this work of the various machinery, such as pump, on the fluid. Okay, so my VM hat, again, that's my VM divided by mass flow rate, which is rho Vs, is equal to G Z2 minus Z1 plus my contributions from friction losses, which I'm just going to write them down in terms of values we computed. Anybody knows G in anything other than non-SI units? There are people who do. I have to look it up. So this is approximately 2830 feet square per second square. And then my actual power that I require to pump this fluid is so this is mass flow rate. So I need rho, which was 62.5 times average V times the computed power hat, and I also need times conversion to watt. And I'm just going to write down that number, which is again a lookup number. And one gets about 1.5 kilowatts. So again, what was not necessarily straightforward in this chapter was coming up with these energy balances, and we didn't spend a lot of time kind of wade through those proofs and coming up with the formula. But then once you have a formula and you have these tabulated values, what you need to remember always is check the Reynolds number. Okay? And write it down now for your exam or whatever comes up. If you have a porous medium and it appears that you have an impulse to use Darcy's law, still check the Reynolds number. Okay. Double check that Darcy's law is actually applicable. If it's not, then you have to go to Ergun equation and add those velocity terms that have like velocity square in there. Okay? Because those inertial terms become important if you have higher Reynolds numbers. So the biggest deal is approximate Reynolds number so you know the flow regime, and that determines which values you're using in estimating friction losses. That's what it comes down to. Or which formula for that matter. Okay? Because for different formulas, we have different fits to the data. Okay? All right. Other than that, it's relatively straightforward. Okay? All right. We are done with momentum transport. Are you going to be sad? No more tensors? Okay? And we are starting with heat transport. Your new reading chapter is chapter 9. And of course I have to customary change here of swapping displays. All right. Heat transport. Okay. But this is an old, I thought I deleted this slide. Okay, I'm gonna do a quick, we did not skip this. This was from last time I taught. This we did not skip either. Okay. This was done. We are going to go back to time-dependent problems and deal with them at the end for all types of transport because they're extremely similar in the way they're treated. So we have checked off pretty good portion of the of the course topics. And basically, I would argue the most difficult ones are in here. From now on, it should be a smooth ride. So we have energy, heat transport, mass transport, and then after that, we're going to look at the time-dependent problems and dimensional analysis. All right. So just like we had in any type of transport, for transport to happen, we have to have a gradient. Now, in momentum transport, our potential was the difference in pressure, or gradient in pressure. And also what caused our friction along the way is differences in velocities. Okay? And inside of the fluid, these different velocities and local changes in velocities cause internal shear stresses. Okay? Now, and what we have in energy transport, the essential difference that is getting evened out is that in temperature, or thermal gradient. Temperature field in itself is a scalar field, unlike velocity field. So the treatment of this is a little simpler mathematically than it is for momentum transport. Now, that said, the essential mechanisms, or why does this transport actually happen, are very similar. They're ultimately molecular. Okay? And basically, we have temperatures related to the velocity with which, or average velocity with which I have molecules move, especially if I have the fluids. So they have some space to move around, and that's correlated with the velocity. And basically, just through molecular collisions, okay, those higher velocities will get transferred from regions of higher temperatures to those where I have lower temperatures. So essential origin of all of this is molecular, which is very similar to treatment of the momentum transfer. Okay. So just to look at the origins of the thermal gradients on Earth, okay, one thing that we have to think about in subsurface is that we have about 25 Celsius degrees change in temperature per kilometer of depth. Okay. So at 3 kilometers, which is normal, which is called good day in petroleum engineering, you have 75 Celsius degrees. So if you're in Texas, the surface could be 40 Celsius degrees, right? It's 25 Celsius degrees in winter and 40 Celsius degrees in summer. However you turn it around, you're going to be at the boiling temperature for water anyway, at 3 kilometers of depth. So that's something to definitely think about in terms of what is the state of the fluids at that temperature. Right? What are their properties? We know that viscosity will change. We know that we have phase changes, even more importantly. So that's something to be taken account. Now, on Earth, we actually have at the core partially molten rock that is at temperatures from 650 to 1200 degrees Celsius. Okay? And that's postulated to exist everywhere beneath the Earth's surface, somewhere at the depths of 80 to 100 kilometers. Postulated because nobody has been there. But we do have lava that here and there surfaces to the Earth. That's one. And second thing, we have seismic studies. And from seismic studies, we see that shear waves don't get transferred, but that means that they're going through liquid and not through solid. Okay. Now, the temperature at the Earth inner core boundary is estimated to be 5,000 kelvins. Okay. So that's the actual inner core again that we've never gone through. So that causes a mean heat flow, and because of the different materials, we're going to have a different mean heat flow over continental crust versus where I have ocean on top of it as well. Okay, so that's just some of the origins. Now, to zoom in a little to what petroleum engineers care about, this is just like an example of thermal gradients that have been. I grabbed it from the following paper. just to give you an example of what gradients in temperature in degrees Celsius per 100 meter are estimated from bell logs. Okay? So it's not huge differences, but I have, so in this particular case, it seems that I have, for the most part, 3 to 4 Celsius degrees variation in temperatures. But here and there, that might actually make a difference. Now, what's the difference? Well, what is the type of oil that I have at certain temperature? What has been the maturation history? That's something that has to be estimated. Second thing is that, so this is what's there to begin with, and that's not something that we have influence over. But petroleum engineers come in with their operations, and we're going to inject water. Okay? We are going to produce fluids, inject water, inject all other types of injectants, and those injectants typically have surface temperature, which obviously is way different from what's down there. Okay? So we're going to induce thermal gradients. Most importantly, they're going to have going to influence mechanics, geomechanics of the rock itself. They might help with hydraulic fracturing, for instance, because they additionally stress the rock in addition to the earth stresses that we have down there. So again, introducing thermal gradients with whatever fluid it is that we're injecting at a time, from drilling fluid over to water flooding or whatever enhanced oil recovery technique we might be applying, we're going to induce thermal gradients. That's something to think about. Okay? Or it could be even steam, which in that case, it's not a huge thermal gradient when we're injecting steam, depending again on the depth of injection. So something that we just want to recall that we had in momentum transfer. Okay? So this was my equation of motion, right? That soup of vector values. So what are the contributions that I had in there? Convective is the first one. Is the actual gradient of pressure driving it. Shear stresses and external force. Okay? So those are the things that can change momentum. Okay? So we have these three. And in essence, I'm going to have flux when we actually have a gradient of potential. So the relationship that we had that was very important to estimate in these stresses is a linear relationship in my shear stresses. So that is the simplest one we could have for Newtonian fluid. So just to recall, so shear stresses are, so my shear stress in the very simple case where I have sort of one-dimensional case because we were looking at only one velocity that was transferring across only one of the directions, we had this linear relationship between shear stress. So this is my coefficient of proportionality, and these are my gradients that are driving the whole thing. Now, we had to have a tensor because velocity is vector field. It's going to be a little simpler here. So let's see what do we have in energy transport. Now, mechanisms themselves remain molecular. Okay, so we're going to have molecular motion, which is the key mechanism. We're going to have convective, so some of that will simply be carried into my volume, whatever control volume I might be looking at. So some of the heat is simply transferred by bulk motion of the fluid. And diffusive, so this is basically just by interdiffusing of mixtures of different types of molecules. They are going to carry their energy with them. So that's not something that we're going to directly cover. Also, we're not going to cover radiative. So in radiation, I don't need any medium. Okay? So I don't necessarily need molecules to transfer heat. Now, what is our Fourier's law? So we're going to, again, have the simplest case. And the simplest case will actually be without motion of fluids at all. Okay? So I just have a material, some plate of some material, and that plate has thickness y. And I'm going to impose different temperatures on top and the bottom of this plate. Okay? The plate has area A. So let's just, before I actually go through it, so let's think about the heat transport. So I know now on top of my plate, I have molecules that are moving much faster, where it's, let's assume that it's a higher temperature up there. And on the bottom, I have lower temperature, so molecules are moving much slower. Okay? And there's certain thickness of the plate. So if I increase the difference in the temperature themselves, okay, how does that affect my heat flux? Increases. So I'm proportional to the difference in temperature. If I actually increase the thickness, so now I have double the plate to go through, how am I going to affect heat flux? Decrease it. So it's inversely proportional with the thickness. And if I increase the area, okay, how am I going to increase? Because I'm basically just add. Okay. So I'm proportional to the area, proportional to the temperature difference, and inversely proportional to the thickness between the plates, or how far do I actually have to transfer. So when I put them together and actually put some numbers, so I could call them T0, T1, I'm going to eventually, after waiting for some time, develop a steady state profile, and my flux per area, so this is basically saying flux is proportional to the area, is some coefficient, okay, and proportional to the delta temperature and inversely proportional to the thickness of the plate. So that's all there is to it. Okay? Now, I will have to, so my K, or proportionality coefficient, is called thermal conductivity. So I, of course, depend on that material too. So if I put a piece of wood, or if I put a piece of metal, what's going to happen? What do we know from experience? Right. So if I want to insulate, I'm going to use wood or styrofoam or something that doesn't conduct heat all that well. Okay? And that's why all of our coolers are from styrofoam. And they're all, who knows what is inside here. I didn't open it up, but there is actually some insulation so that my coffee, though by now my coffee is cold, so oh well. I'm drinking it anyway. But so that's basically just slow the things down. It's not going to stop them, but it's going to slow them down, because the thermal conductivity of the material we are using is hopefully insulating. Okay? And one thing that is missing here, if I was thinking about this in coordinate system, what am I missing? The minus. Why? Because again, I'm always going to flow from higher temperature to lower temperature, but all of the coordinate systems I know are pointing from lower to higher. So my vectors are always pointing from lower to higher. My flux is always from higher to lower, which is causing a minus in this relationship. So when I send this thickness of the plate to limit of 0, I'm actually going to get a derivative of temperature with respect to y. So this is essentially, here I have only one direction that I'm considering, but this is essentially a partial derivative in y direction. Okay? So my flux in y direction, which I'm looking at as quantity per area, and whenever I'm actually looking at the total flux, I'm going to have to integrate over an area, that qy is minus k dt dy. Cool. So this is what we know already, really. Not much has changed. So that's it in 3 dimensions. Now it's actually much easier to look at it. I don't have to look at transport across 3 different planes and whatnot. Okay? So my qx is minus k dt dx. So basically, partial derivative, these should be partial derivatives of temperature with respect to x, y, and z. So my flux is a vector quantity, okay, that is proportional to the gradient of temperature. Okay? Now this is isotropic case. It's assuming that there is no differences in thermal conductivity as I look at different directions. Okay? So in that sense, my material seems to be same in all directions. Sometimes that's not going to be necessarily the case, specifically in solid materials that might be built from something that in itself has heterogeneity. So it might be actually built from material that is not homogeneous everywhere, but it has certain structure to it, like a porous medium, foam, types of foams that might have, for instance, cells in the foams inside that are elongated for some reason. Right? That's going to give me different values in along those cells versus across from them if they're different shapes in different directions. So there's various ways, but those materials by themselves are not homogeneous. They have some structure to it that is imparting different conductivity in different directions. In terms of geologic materials, typical heterogeneous materials that are kind of built from plates like that could be some of the shales if they actually have, or some of the clays if they actually have plate-like structures within. Because clays can have platelets, and those platelets are kind of aligned in certain direction. So cross direction versus a long direction will have different properties, both in terms of conducting fluids, permeability, and in terms of thermal conductivity. Okay, so in anisotropic case, most general case, this conductivity is actually sort of a tensor. Okay? And this tensor is applied to the vector, which still gives me vector Q as a result. Okay? Now, in terms of units, okay, I have energy per time per meter squared. That is in terms of flux. And then I have to multiply it by this spacing y and divide it by temperature T. So these are ultimately my units. I can either look at it as joule per meter Kelvin second or watt. So joule per second is watt per meter Kelvin. And then we're going to look at the thermal diffusivity, okay, as a normalized version of the conductivity, thermal conductivity. And this one is in meter square per second. And it enables us to look and compare different types of transport. Okay? So I can normalize viscosity. Okay? I can normalize thermal conductivity to meter square per second, which enables me to compare different types of transport. So what are we normalizing? We're also normalizing by rho, just like I can normalize viscosity to kinematic viscosity. And also thermal capacity per unit mass at constant pressure. And those are tabulated values. So when I do that, again, I'm going to get units of meter square per second, which are equivalent to the units of kinematic viscosity. And we're going to look at that. Like, that's basically what part of the dimensional analysis is kind of normalizing things and comparing different types of transport. Why? Why do I want to normalize? Why do I want to compare? So I need to basically order or figure out what is my dominant mechanism. If there is a dominant mechanism, as in 1,000 times Vince, if my momentum transfer is 1,000 times over heat transfer, over the time scales that I'm looking at for the problem, heat transfer might not matter. And one thing that we will learn as we start solving is that we can barely ever solve all of the types of transports at the same time. So we kind of have to freeze. Right now, so far, we've been looking for everything in momentum was isothermal. Okay? But that essentially means that I'm freezing at certain temperature. I'm taking my viscosities, whatever they are, right? And I'm just assuming my constant temperatures or that it's not changing enough to affect my viscosity. Okay. Now, then maybe if it's changing, I will actually adapt to a new viscosity value and then compute again and kind of freeze for the time being and move on. But for that, I also assume that my momentum transport in itself is winning over heat transfer. So that the changes that I might have in viscosity are relatively slower or happening at a different time scale, slower time scale, compared to those for momentum transfer. And if I have turbulent flow, okay, through some large pipe, that's not so difficult to predict. Right? That's convection through is winning. Right? So in that sense, we kind of have to always evaluate who's winning, who is the dominant type of transport, so I can actually be practical and solve in practical situations. So the numbers that actually quantify that, one is called Prandtl number, so it's momentum versus energy transport in the flow system, which is basically looking at those two normalized coefficients in meters squared per second when I divide kinematic viscosity with alpha, which is thermal diffusivity, okay? They're both normalized to meters per second. I'm going to get Prandtl number, okay? Another one is Peclet number, which is somewhat more in practical use when evaluating flows. And this is Peclet number for heat transfer. We're going to have another one for mass transfer. So that's basically the bulk advection of heat versus temperature gradient diffusion. Okay? So my heat might be simply flowing in at much faster rate than it actually diffuses. Most of the equations we're actually going to apply here, we'll have both of those. There will be convective part and there will be just diffusion part. Your favorite problems to solve will be those without convection at all. Those are the simplest. So that's solids, right? So in solids, I don't have convection. So this is my Peclet number. And for common values, we're going to take a look at the values in VSL. I have tables coming up. For gases, there is table 912, 913, 915. So let's just do a guessing game before we look at them. Any idea of what this Prandtl number in terms of momentum transfer winning over? Again, so this is momentum versus energy transport ratio. For gases, water, glycerol, and earth mantle. Just throw in a gunky fluid at the core of the earth. Roughly? Order of magnitude? I'm looking for order of magnitude.
The highest the earth mantle is the highest. Okay. Well,
I like that approach. All right. That's a smart approach. Earth mantle has the highest. Sure. Gases. Things should be, think about kinetic theory, molecules bouncing around. They can be the same, right? If I have really those little tennis balls that are moving around, and just the elastic collisions between them, they're kind of on the same, right? So it's about 0.7 for gases. For water, it's about 6. So over 6,000. And earth mantle. So basically, the more viscous system I have, the momentum transfer wins over diffusion. These are actual numbers. They're a little hard to look at. So these are my Prandtl numbers for common gases. Let's look at some behavior that we typically care. So we looked in our heat flux. There's only the temperature difference that is playing a role. However, the K, the thermal conductivity in itself, could depend on the absolute temperature. So for the flux itself, I kind of assume for the given temperatures that my thermal conductivity is not, that gradient is not so large that I can take thermal conductivity as a constant value, but that constant value could be different at different temperatures. Even though for flux itself, I'm really looking just at the differences. So yes, there is a difference whether my difference could be 100 kelvins, okay? 100 Kelvin to 200 Kelvin, and 300 to 400 Kelvin, okay? Those are two different systems in terms of the thermal conductivity itself at those two temperatures is typically different. So let's see how different, okay? So it could be for the one of the simplest gases, it could be twice, between 100 Kelvin and 300 Kelvin. Okay? For methane, also about more than twice, 3 times. Okay? So it does matter. It's also a pretty large gradient. But Prandtl number, give or take, stays around 0.7 to 0.8. Okay. Now this is some non-metallic liquids. Okay. So there's my glycerol right here. As I heat it up, my viscosity goes down. As my viscosity goes down, so does the momentum. Importance of momentum transfer versus heat transfer goes down as well. So that's quite a sizable difference between just like 300 and 400. Now, do I have a rule? So I have, with increase in temperature, I have decrease in thermal conductivity for 1/10. Decrease, decrease, slight increase, slight increase. It's a toss-up, okay? And you will guess, if you remember viscosity, it was hard to come up with a good theory for viscosity, to explain viscosity from fundamental rules for gases and for liquids, specifically for liquids. And similar is true for thermal conductivity. So again, here I can see that I have a toss-up in terms of whether it increases or decreases. So we're going to continue on Friday.